Okay, in this first review section, we're going to go through some things pretty quickly. We're going to talk about domain and range of functions. We're going to talk about graphing functions, increasing, decreasing as adjectives for functions, odd, even functions, some proportionality stuff, inversely proportional stuff, the basic power functions, and then some adjectives to describe what types of functions that we have. So let's get started with the domain and range. So the domain is the set of valid inputs in a function. Right, so we avoid three things. We avoid division by 0. We avoid square roots of negative values, right? Even roots of negatives. And then 3, we avoid logs of not positive things. Okay, and those are the three things that we need to avoid when we're computing a domain. For example, we'll just do a really simple one. The domain of, let's say, 1 over the square root of x. So I need to avoid negative things inside the square root, so I can't have x being negative. I need to avoid division by 0, so I can't have x being 0 either. So the domain of this is strictly positive x values. So the domain of f of x is bigger than 0. Okay, the range is the set of possible outputs. Okay. So the range of the same thing, f of x equals 1 over the square root of x. Well, I can only get positive things out of the square root, so the range of this function is at most all of the positive numbers. It could include 0 too, but it does not include 0 because I can't divide 1 into small enough pieces to call it 0 at the end. I would need to divide by infinity, which that's not a thing that we can do. So the range is y is bigger than 0 is the range of this. I can get any positive number out as the range. If I want really big positive numbers, I put in really small x values, right? If I want really small positive values, I put in really big x values. So I can get anything between 0 and infinity. I can't get 0, I can't get infinity. Okay. So now let's talk about graphs of functions. So graphs are pairs of input-output coordinates, right? Input-output pairs. And we plot those input-output pairs in the Cartesian coordinate plane, and we connect them all together, and that gives us the locus of the graph. So the collection of all points x comma y in the Cartesian plane that satisfy f of x equals y, right? So if I use x, I get y as the output, is the graph of f of x. So let's just take a little simple graph here. Here's x equals y as the graph, and any point on here is going to satisfy that the x coordinate and the y coordinate are the same, right? If this is my function, f of x equals x, and we have that be our output. we get this graph. Okay. Sometimes we have piecewise functions, and that just means the domain has different pieces where I do different rules on the pieces. It's still a function because every input only belongs to one of those rules, and we get the graph that way. So let's look at, say, f of x equals x if x is bigger than or equal to 0, and negative x if x is less than 0. Okay, so I've got two parts of the domain here. I've got the less than or equal to 0 part, and I've got the bigger than or equal to 0 part. So let's see if we can graph this. I'm going to break the x-axis into those two domains. The blue domain is the origin and everything to the right. The green domain is everything to the left here. Right? Gets all the way up there but doesn't include 0. Okay, over on this green domain, I take my input value and I make it negative. All of these input values start out negative, so when I make them negative, they become positive. But it looks like they take the same value, this distance in the y direction, and the distance in the x direction is the same on this graph. Okay. For the blue part, I just get exactly what I put in, so I get the same thing here. The distance from the x direction, the distance from the y direction is exactly the same. This is my absolute value function. We'll draw that complete graph in white then. It comes down, bounces off the origin, and goes off in both directions. This is piecewise because I've got two different pieces of the domain that do different rules, right? The blue thing, the blue part, the bigger than 0 or equal to 0 satisfies the rule that if I take my input, I just send it right back out. But the green part, if I take an input that's negative, I have to send the negative of it right back out. So I've got different output rules, x or minus x, depending on which piece of the domain I belong to. That's why it's piecewise. Okay. Let's do increasing and decreasing. Well, let's go back to this picture. Half this graph is increasing and half this graph is decreasing. Increasing means if I move to the right, I'm moving up. That's increasing, right? We're always thinking about moving to the right because my inputs are moving to the right as I go from negative to positive. If I move to the right and I go down, this is decreasing. So up and to the right is increasing, down and to the right is decreasing. This is down and to the right, decreasing. This is up and to the right, this is increasing. At this point, it's flat. Okay. Odd, even. So these get their name from the power functions like x squared and x cubed. If the exponent's odd, you have an odd function. If the exponent's even, you have an even function for just the power things. If you've got a combination of like an x squared plus an x cubed, it's not odd nor even because you get this mix of things. Sometimes the combinations can be odd or even, so we've got to generalize that a little bit. Odd basically means that the minus sign can come outside. So if f of minus x equals minus f of x, then f is odd. This has to be true for all x values. Okay, for even, the minus sign gets absorbed. If f of minus x equals f of x with no minus sign anymore, then f is even. And this also has to happen for all x values. So let's see some examples. X squared is even since f of minus x equals minus x squared equals x squared equals f of x. Right. X cubed is odd since f of minus x equals minus x cubed equals minus x cubed equals minus f of x. Okay. F of x equals x squared plus 1 over x cubed minus x. What do we think this is, odd or even? I've got some even stuff, I've got some odd stuff, maybe it's neither. This one's odd. Let's see how that works. So f of minus x equals minus x squared plus 1 over minus x cubed minus x. The top doesn't change at all, right? X squared plus 1. The bottom, that minus sign sticks around and that minus sign sticks around, so everything on the bottom is the negative of what it was before. And that minus sign out front of the bottom can be pulled all the way out front. So this is minus x squared plus 1 over x cubed minus x, which is minus f of x. So this is odd. Okay. Proportional. So let's think of speed, time, and distance, right? So I'm going to have, let's say, speed times time equals distance. So if I'm going 5 miles an hour for 1 hour, I'm going 5 miles, right? That's how this thing's related. Well, if the speed increases but the time stays the same, then the distance increases. So speed is proportional to distance. It's kind of like a fish symbol. Okay. Time is also proportional to distance. If I go the same speed, then if I increase the time, I increase the distance. Time is proportional to distance. Okay. So if one of these increases, the other one increases. If the distance increases and the time was fixed, then the speed increases. If the distance increases and the speed was fixed, then the time increases. So these guys are proportional to each other. Okay. Speed and time are inversely proportional. Speed is proportional to the inverse of time, or I could write it as time is proportional to the inverse of speed. Okay. Inversely proportional means that if one increases, the other decreases, right? So if I speed up, it takes me less time to go the same distance, right? Or if I slow down, it takes me more time to go the same distance. So that's how proportionality works. These guys mean that if I took time times some constant, k, the proportionality constant, I would get the distance. These guys mean if I take time and speed and multiply them together, I get that proportionality constant. So the proportional, if they're proportional, the variables are on opposite sides of the equation with a proportionality constant next to one of them. Inversely proportional, the variables are next to each other with a proportionality constant on the other side. Okay. We talked a little bit about power functions. Let's do graphs of power functions real quick. So I've got f of x equals x. That's just a straight line, right? F of x equals x squared. That's my basic parabola. F of x equals x cubed. That's this kind of curvy guy. He starts out down and left and goes up to the top right. Okay. F of x equals x to the fourth. We get that parabola again, sort of deal. Okay. What I'm going to do is I'm going to say f of x equals x to the n. And then we're going to have two graphs. We're going to have a graph when n is odd, and we're going to have a graph when n is even. In odd, I'm going to start down and to the left over here. I'm going to end up and to the right over here. And how I get there is I go through like this little curvy bit, right? In here, there's a little box between 1 and -1. Okay, the bigger the n value, the closer this looks like to coming up to this point here, going straight across, and then going up that way, right? So, the bigger the n value, the sort of more square this angle making bit is at this angle and at this angle. Same thing with even, only with even I've got that little box here between 1 and -1. Even, I want to come up this way, and I want to come up this way from when I first get to the box, and then it's going from this point to this point across the box. Okay, so even, the bigger the n value, the more square this bottom is, right? The bigger the n value on the odd, the more square this corner is. Okay. And then some adjectives. I've got polynomial. Right. Every term has whole number exponents on the variables. Algebraic. Every variable has a rational number on the exponent. Finitely many terms. Exponential, you've got variables in the exponents. Logarithmic, they're the inverses of exponentials are involved. And trigonometric, we've got the basic trig functions are involved. Well, any trig functions. Okay, so that's the ideas behind all of section 1.1. We'll do 1.2 in the next video. I think it's a little shorter.